The first talk is strong IND-CPAD security for FHE, essentially for free, and Marc Joye will give the talk.
So hi everyone. So for those who came last year at FHE.org, so maybe you remember, but at that time, we were already discussing those IND-CPAD attack. And so what I'll do in this talk is, and hope you learn how to protect against those attacks. And what is nice, as you'll see, is that it's essentially for free. So as you know, one of the main challenges we have when playing with FHE is the noise. So we need noise for security, but at the same time, so when we operate on the ciphertext, so the noise tends to increase. Related to that is also the notion of failure probability. So something also you want to have is that when you decrypt a ciphertext, of course, you'd like to get the correct corresponding plaintext. And so what is difficult in FHE is to find the best trade-off between efficiency, security, and correctness. And so in this talk, so we'll try to answer 3 questions. So the first one, so what's the impact on decryption failures on the practical security? So if you attended CCS last year, so there was a nice talk on way to turn decryption failure into attacking the IND-CPAD model. And one of those attacks was even a key recovery attack. So you see that that notion of failure is not only a correctness issue, but also a security issue. And what does that mean? It means that in practice, so if you want to have security in that IND-CPAD model, so you have to lower that failure probability, I mean, very, very, very low. And typically, so if you want to target the 2D-128 bit security, so you should have something similar for the correctness. So of course, we'd like to have an efficient solution. So how to do that, but without impacting too much or even without impacting the performance. And last question I'll try to answer is, what is the impact of the technique we propose in theory and also in practice? Okay. So you'll see that the main notion that is central in this work is the notion of drift. And drift, so it's maybe a fancy word, but basically it's just the noise you have when you mode switch a ciphertext. So you have a ciphertext which is defined mod some modulus, and during the computation, so you have to switch that modulus to another one, a smaller one. And because you are doing that operation, so at the same time, you're also introducing error, and this is due to the rounding. And because of that, so it means that the noise will increase. So does that matter? So answer is clearly yes. Because so in the basic IND-CPAD model, so the problem is, as I said, failure probability also has an impact on security. So you need to control that noise. There is a very easy way to prevent those attacks. You just have to increase everything. So you take larger parameters, and then you should be fine. But the price to pay is pretty huge, because then, I mean, your implementation becomes less and less efficient. So what are the security notions we are using currently in FHE? So the very basic one, so IND-CPA. So that's the standard security notion we ask for any encryption scheme. So that's the basic one. So you need that one, otherwise it's not, there is no crypto. So basically, it works as follows. So you can choose to plaintext. I give you back an encryption of one of those two plaintext, and you have to tell me which one it is. And so it is secure if the best strategy for you is just to guess at random. Okay? So basically it means that, so in CPA security means basically that ciphertext give you no information about the corresponding plain text. Okay? So that's the basic one. So that's enough for some applications. So think, for example, of a basic client-server application, so where everything is encrypted under the client's key, and so the client gets back some ciphertext encrypted under a key. So, I mean, in that case, IND-CPA can be enough. For some other applications, that's not enough, so we need more. And so the next notion is called IND-CPAD. So it's IND-CPA, but with a decryption oracle. So as you know, so we cannot get chosen ciphertext security for FHE, but still you can give access to a decryption oracle if you restrict the access. And in this case, so an attacker can only probe the decryption oracle if he knows the underlying plain text. Okay? So you may say, well, but in that case, it's not useful. Actually, it is not if the scheme is exact, but if it is not, so the attacker may have the information that there was a failure or not during the decryption. And that may be enough to lower the security of the scheme. And there is an even stronger notion, so that we introduced in this work. It's called IND-CPAD, so with a S, and S is for strong. And the idea behind that new notion is to capture the fact that in real life, so so assume you're publicly encrypting a ciphertext, then you can choose the randomness by yourself. And if you look at the way this is done in the IND-CPAD security game, so the randomness is chosen by the encryption oracle. And so we show that this new notion is stronger and is different from IND-CPAD. So you can have a scheme that is IND-CPAD secure, but totally insecure with that new notion. Yeah, so IND-CPA, so again, so depending on the application, cannot be enough because when you have a failure in the decryption, so you may get some information about the secret key and then break the security assumptions. So again, that really depends on the application. So the problem is that the noise accumulates, so when you are operating over encrypted data, and if at some point so you see that there is too much noise, so what you have to do then is to apply what is known as bootstrapping, and that will reduce the noise at a nominal level. But the problem is that if you look at scheme like FHE, TFHE, or final, one of those operations, so during that bootstrapping operation, is a module switching. And because of that, so you get some drift. And so something you'd like to avoid is that the noise exceeds some threshold, because in that case, so the decryption will fail. And again, so that can be used by an attacker. So the practical impact is that an attacker, can always craft a ciphertext and then use those ciphertexts to probe the decryption oracle and hope for a failure. And so to get IND-CPAD security, so it means that you need to control that failure and have all the steps protected. So you want to be sure that all the steps in your computation are exact. So give you the correct, give you the correct, correct decryption. So to recap, so ciphertext drift. So when you mode switch, so this is done by by rescaling and rounding. So that will introduce some noise, and that noise increase the probability that there will be a failure when decrypting. And again, so that's an essential step in the, so for Bootstrap FHE, like View, Final, and anti-FHE. So what to do? So if you have parameters that were designed to get IND-CPA security, that does not mean that you'll get IND-CPAD security. So you have to find a solution. So the easy one is just to increase the parameters, but we'd like to have something better than that. So what we do in this work, so we have two types of contributions. So first on the theory side, so we introduce that new notion and we show that it is different from the current IND-CPAD security notion. And we also characterize the failure probability of in practical FHE schemes. And the second contribution, and I'll put the focus on that one in the rest of the talk, is a new modulus switching method. And as you'll see, that's a very easy way to control the noise and to reduce the failure probability. And what is super nice about that is that the price to pay is very low. So there is almost no impact on efficiency. So let's take an example. So this is the basic LW encryption. So a ciphertext is just a series of AI, so random values mod Q, and the body B. So you use those mask value and the secret key SI to mask the message M. And you see that there is also some input noise E in. Mode switching so means that you have to reduce that ciphertext mode, let's say 2 times n. And so what you do, so you rescale all those elements, all those AI and the body B. So you divide by Q, multiply by 2 times n, and then you round. So if you now look at the rounding error, so you can always write all those alpha I like the rescaled one, so A I tilde times Q over 2 times n minus some rounding error alpha I, same for B. And if you now look at the error you get at the end, so of course there is the input error that is there, plus an additional one that is the drift error. So beta minus the sum of alpha I times Si. Okay? So the goal is to try to minimize that error. And we make two observations. So the first one, so given a LW ciphertext, so AI and B, so it's quite easy to randomize that ciphertext, so you just have to add the random encryption of 0. Okay, so you'll get another ciphertext that encrypts the same plain text. And the second observation is that the drift vector, so that vector of alpha I and beta, so anyone can compute that vector. There is no secret involved there. So the drift error is secret, private, but not the vector. Okay? And so the idea is quite simple. So what we do is this. So you have your input ciphertext that you have to mode switch. And what you do, so you just add a random encryption of 0 to that ciphertext. And the hope is that that new ciphertext will behave better regarding the drift. Okay? And so we need also some tests to know whether the ciphertext you get is better or not. So, and for that we'll use the drift vector. So remember that one can be publicly computed. Okay? So you are given ciphertext, you add an encryption of 0, and you test if the new ciphertext is better regarding the drift. So I still have to explain you how to do that. So there are different options. So I'll just present one. So assume that you are given some ciphertext C, so an LWE ciphertext. The drift vector is alpha I and beta, and the corresponding drift error is beta minus the sum of alpha I times Si. So now if you look at the average value for the drift error, so we get that expression, and same for the variance. So you see that, so in this case, you assume binary keys, but I mean, you can do the same for other key distributions. And so we don't want the drift error to be too large. So something we don't want is to have the drift outside that range. And that is given by the RFC function. And so just remember that if you take R equal, I mean something about 13, then the probability that the value is not in that range is 2 to the minus 128. Okay? And so here is the test we use. So we check that the absolute value of mu plus R times sigma is smaller than some threshold T. And so that threshold is, of course, application dependent, and this is the maximum drift error you can tolerate. Okay? And so you just add encryption of 0, you apply the test, and if the test succeeds, then you get, you have a good candidate. Yeah? So how does that work in practice? So how many times do you have to repeat? And surprisingly, not much. And here is an example. So those are 4 parameter sets. So the first 2 ones have a failure probability of 2 to the minus 40. And the 2 last ones have a failure probability of 2 to the minus 64. Yeah? And so if you apply the previous test for the 2 first sets, so the first one is for Boolean values, and the second one for plain text of 4-bit payloads. So if we apply the previous test on the 2 previous sets, and you do it at most 100 times, so you'll get a good candidate. And that will give you a failure probability of 2 to the minus 18. So you start using the regular module switching with a failure probability of 2 to the minus 40. And then when you apply that new mod switch, so when you add an equation of 0 and then you test, you get a failure probability of 2 to the minus 18. Yeah? For the 2 last sets, it's even better. So if you repeat at most 50 times, so you'll get, so you start with a failure probability of 2 to the minus 64, and you end up with a failure probability of 2 to the minus 128. You see? So the price to pay is that you have those additional mod switching, but this is almost for free. I mean, that costs nothing. So just roundings. So compared to a blind rotation, so I mean, you can neglect that cost. If you have a failure probability of 2 to minus kappa and apply the new module switching, so then you get a failure probability, I mean, about 2 to minus 2 times kappa. So that's, I mean, pretty good. So it gives you an exponential improvement in the failure rate. As I said, so there is almost no performance penalty, and you have much better security guarantees. So you have security in the IND-CPAD model, so for example for the 2 last sets, and even security in the strong IND-CPAD model. So if you like the topic, and I hope you do, okay, it's okay. So here are some research questions. So the first one, So is there a better way? So what we do is just add a random encryption of 0, but maybe there's a better way. So maybe instead of just trying at random, so maybe you can construct such a solution. So maybe you'll find a clever way to do that. Another question, so what you observed is that, so if we start with a failure probability of 2 to the minus kappa, so we end up with a failure probability of 2 to the minus 2 times kappa. Is that an optimal bound, or maybe is there a better solution? So, I mean, we don't know. And a last question, so because now that we have that technique, the technique is pretty generic, can we apply it beyond FHE? So, I mean, that would be nice to find more application now that we have that, that new trick. And this is my last slide. So just to sum up, so what we did in this work, so we did study the ciphertext drift in FHE. We did propose a new mode switching, and the goal was to reduce the failure probability. And we also introduced a new security notion to refine the IND-CPAD notion. And thank you.
We have time for a few questions.
I would like to just make one comment about ciphertext randomization technique. And if I understood correctly, you're basically looking for some encryption of 0, which share almost the same LSB as in the input ciphertext. So I think you can just search for encryption randomness using some lattice algorithms to find this closest vector to the target ciphertext.
So you just saw the first research question then?
Oh, this is a comment. Yeah.
Thank you. Great talk, great idea. I have a question. So in the title it says it's for FHE. So to me it looks like so far the focus is on FHE and TFHE, where essentially modular switching error is the main error. As far as I understand, in BGV, BFE, CKKS, there might be other contributions as well. And just what are your thoughts on extending this to other FHE schemes before going outside the FHE domain?
Okay, so the main focus was on that family, so FHE, TFHE, final. But you know that trick of just adding a random encryption of 0, I mean, you can apply to many settings. So the difficult step is to find that what we call a quality test. But I mean, if you have such a tool available for any, it's not only model switching. I mean, it could be anything, even used in FHE. But if you have such a quality test available, then you can just do the same. So think, for example, I don't know, to a key switch, or all those operations that you are using in FHE. So beyond just that modulus switching that is used as part of the bootstrapping in those schemes.
More questions? So let's thank Marc again.
Thank you.